Well, hello and welcome again to Math 315, Analysis and Topology. And in this section we're going to look at two different topics, firstly on Cauchy sequences, and then we're going to move on to look at the question of differentiability. Now this first section on Cauchy sequences is a little bit difficult. Main point is if you can follow through the arguments, and then I will show you some examples of the sorts of things that you may need to be able to do. So we're going to leave continuity for a while, and we're going to return to the question of sequences. So far most of the sequences we've examined were monotone, that is, they were either strictly increasing or decreasing. And in that case, if they were bounded as well, then we could use the monotone convergence theorem to claim that the sequence converged to something. Now in practice, not all sequences are like this, and we'd like a little more theory to deal with sequences which are not monotone and yet may nevertheless converge. And it turns out that to study such sequences we need this notion of what's called a Cauchy sequence. This is named after Cauchy, who was a French mathematician who, along with Weierstrass, were really the founders of modern analysis. So a sequence A sub n is called a Cauchy sequence. Well, what does it mean? It simply says that the terms eventually are becoming arbitrarily close together, and not just consecutive terms, but any of the two terms can be made, the difference can be made as small as we like, provided we go far enough. That is, given any epsilon bigger than naught, there is a positive number n, which depends on epsilon, of course, so that if I take two terms beyond there, take two integers beyond this capital N, then the difference between these two terms in the sequence, not necessarily consecutive, is less than epsilon. So what it says is a sequence is Cauchy if eventually the terms, any two terms, become arbitrarily close together, provided I go far enough. Now, I just mention again that in most books they insist this capital N be an integer. We may as well just take n to be a real number, and then we simply think of the n and m as being the next whole number after that one. Now, it turned out that the notion of Cauchy sequence was just the right condition for convergence of a sequence. Now, before doing this, we'll just do a simple example of a Cauchy sequence. We're going to prove that this sequence 1 on n is a Cauchy sequence. Of course, we've seen the sequence before, it converges to 0. So to prove it's a Cauchy sequence, well, we take any epsilon bigger than naught. We'll hold this for a minute, and then I take m. We generally take, it's m and n bigger than capital N, but I'm going to generally take m bigger than n or n bigger than m, doesn't matter. So I'm going to take m bigger than n here, bigger than capital N. Then the difference between these two, well, this number is bigger than n, so this is going to be smaller than this one. So when I subtract off something, I'm going to get it less than just 1 over n. And now my little n is bigger than capital N, so I can say this is less than 1 over capital N. And once I've got that, I can choose that to be my epsilon. And I simply solve this again for capital N, and I put 1 over epsilon there. So that's just a simple example of proving a very simple sequence is a Cauchy sequence. Now the main theorem, which is theorem, in fact, 6.4, we're in chapter 6, says that a sequence of real numbers converges if and only if it is a Cauchy sequence. Now that's very interesting, because this, in fact, now gives me a complete condition on when the sequence converges. It has to be a Cauchy sequence, and if it's a Cauchy sequence, then it converges. So I'll just do a little proof of one way round of this to see if you can follow through the argument. So firstly, I'm going to suppose that it converges, and then I'm going to show that it's a Cauchy sequence. So if it converges, so an goes to some limit L, Then going back to our earlier definition of what we mean by a sequence to converge to a limit L, if we're given some epsilon bigger than naught, then there is a positive integer n, so that if I go past there, for all n bigger than capital N, the difference between the sequence and its limit is less than, well, I put epsilon over 2. You've seen this before, just to make the argument come out neatly at the end. Could have just put epsilon here, but I can replace that with epsilon on 2. Now I want to show that this is a Cauchy sequence. So if I take n and m bigger than this capital N that I've got from here, and I look at the difference between two terms, the nth term in the sequence minus the nth term in the sequence, and we do our usual trick. I'm going to subtract and add L. We know this limit exists because that was our supposition, so I'm going to subtract and add L into this. And then as usual, I'll bracket these together, and I'll use the triangle inequality to say that's less than the first one plus the second one. Now this one here is less than epsilon on 2 by our assumption, and the m is also bigger than that, so that means this term also is less than epsilon on 2. We add those, we get epsilon. So this shows that a convergent sequence is a Cauchy sequence. Convergent sequence is a Cauchy sequence. The converse, which is more important, but it's much more difficult to prove, and I'm not going to go through the proof of that here. Again, it relies on properties of the real numbers, so I'm not going to go through that, but that's the converse of this. So this theorem is very important. It says a sequence converges if and only if it's a Cauchy sequence. Now I'm going to do another slightly more tricky example here, but it's important for what follows. Again, I won't expect you to be able to reproduce this sort of proof, but you should try and at least follow it through. We're going to end up with getting a nice type of sequence that we can then deal with, and I'll do some examples of that shortly. So here we want a sequence AN has the property that if I take the difference between two successive terms, these are one after the other here, then that's less or equal to 1 over 2 to the power n. That's just an example at the moment. I take a difference between two successive terms, and that's got to be less or equal to 1 over 2 to the n. And I want to show that the sequence is a Cauchy sequence, and that means this sequence will converge. You can see what this is saying. As n gets very big, this is becoming very small, so it's saying the difference between two successive terms is becoming small, and this is we're going to prove that anything that satisfies this one is a Cauchy sequence. Now here's the little solution to this example here. So here's the condition we've got. We're given that here's our sequence, and the difference between two successive terms, the n plus 1 and the nth, is less than 1 on 2 to the n. So I'm going to choose now n to be bigger than small n to be bigger than capital M, and to check it's a Cauchy sequence we have to look at this difference here. And here I'm taking n bigger than m. So we do our usual trick. I'm going to add and subtract terms. So I'm going to take an minus 1. So I'm going to subtract the term just less than that one, and then I better add it back in again. Then I'm going to subtract the next term, and I'll have to add that back in again. And I keep going all the way down until I have subtracted off the m plus 1th term. I've got to add it back in again, and then I've got my minus an. So I'm just subtracting and adding all the way through, and I'm going to split this up in pairs and use the triangle inequality. Now the obvious reason I do that is because I've got some information on what happens between successive terms. So applying this here now, an minus 1, well, that's the same as this, except n's been bumped down by 1. So that's 1 on 2 to the n minus 1. This next one is less than 1 on 2 to the n minus 2, and this last one is less than 1 on 2 to the m. Now, this next step is just a little bit more, well, the next little bit's a little bit more tricky. What I'm going to do is I'm going to write this just down backwards, that's all. I'm going to start off with this one and write it the other way round. There's a purpose for doing that. The reason is that to go from this term to this term, I'm multiplying by 2 all the time. And so going backwards, I'm going to go from this term to this term, I'm dividing by 2. So I'm multiplying by a half. So this is just a geometric series now. This is just geometric. And the common ratio here is a half when I write it like this. So you multiply by a half each time to get to the next term. Well, this is a finite series, a finite geometric series, so I'm going to say, look, it's less than the infinite geometric series. I'm just going to not stop it here, I'm just going to keep going and adding in all the terms and turn it into an infinite geometric series, because we've got a nice formula for summing that one. And I can sum that, it's a over 1 minus r, so a here is 1 on 2 to the m. 1 minus a half is a half, so 1 over 2 to the m. I'm just going to double top and bottom, and I get 1 over 2 to the m minus 1 when you simplify that. Now the point is, now I've now shown that the difference between any two terms, the nth term and the mth term, when I subtract them, that difference, chasing this through, is less than 1 over 2 to the m minus 1. And I can make this one as small as possible, so I can make this less than 1 over 2 to the capital N minus 1, and then solve it and put it equal to epsilon and solve it. I'm not going to do all that technical thing. I'm just going to say this can be made as small as we like by taking m large enough. In other words, it's therefore a Cauchy sequence. So therefore I can make this difference small. So this one is a Cauchy sequence. A Cauchy sequence. Now that's a fairly difficult example. I don't expect you to be able to reproduce that. But the important point is that what we're doing is we're showing that if I've got a sequence where these differ, consecutive terms differ by less than 1 on 2 to the n, then the sequence is a Cauchy sequence, and therefore will converge. So I should say is a Cauchy sequence, and hence converges. Converges, just to finish it off. Okay, well, another, again, tricky example, but it's a very interesting one, and it's going to lead us to what we're going to call a contractive sequence. So again, bear with me through this and just see if you can follow through the logic of it. So the following example will show us why Cauchy sequences are important. So a sequence AN is defined by, well, we take A1 is 1, A2 is 2, and every term, we put this into English, every term is the average of the two terms beforehand. So I take AN and AN plus 1, take the average of these two, and that's AN plus 2, that's the next term. Now if we look at the first few terms of this, we'll see that this sequence is not a monotone sequence. That is, it's neither strictly increasing nor decreasing. Here's look at the first few terms. We get 1 and 2, well, we were told those two. Now you take the average of 1 and 2, you get 1.5. If you take the average of 2 and 1.5, you get 1 3/4. Take the average of these two, you get 1.625. Take the average of these two, you get 1.68575, and so on. So you can see what's happening. This one's bigger than this one, then it's going less than, then it's going bigger than, then it's going less than, then it's going bigger than. It's not monotone. It's wobbling around, but it looks like it's getting closer and closer to something. And we'll see shortly that it's getting closer and closer to 1.66666 and so on. First we're going to do is we're going to prove that this is a Cauchy sequence. And I'm going to start by just looking at the difference between two successive terms firstly. Not two general terms, but two successive terms. So the an plus 2, I can use the recurrence up here and write that as a half an plus 1 plus an. Now half an plus 1 minus an plus 1 is minus a half an plus 1. So I get 1 half an minus a half an plus 1, and I can take the half out of that and I get this here. Well, now I can just keep repeating the pattern. So look at what happens here. The terms are going down by 1, but then they're flipping around. So this is really minus an plus 1 minus an. So the terms are flipping in terms of the order, but they're just going down by 1, and every time we pick up a factor of a half. So I can just repeat the pattern over and over again, and I can take absolute values now. And then I've simply written down what happens in the first case. Now I can apply the rule again to this one. It's going to bump them down by 1 and then flip them around. But I pick up an extra factor of 2 in the denominator. And I can keep going all the way down until I get down to a sub 2 minus a sub 1. And I've applied that, I've done it n times, so I get 1 over 2 to the n. And finally, I know these two, so a2 is 2 and a1 is 1, so I can just plug those in, and I get 1 over 2 to the n. Now we've just shown a very similar thing where we showed in that earlier example, if we had two terms, consecutive terms, differing by 1 over 2 to the n, then we saw that was a Cauchy sequence. So by the previous example, it's got an n minus 1 or something there. This is a Cauchy sequence, and so it converges by this Cauchy criterion. So this sequence now, that takes every term is the average of the two terms before it. It's not monotonic, but it is Cauchy sequence, and therefore it converges. Now the question is, what does it converge to? Because there's no use, if it converges to some limit L, well, simply putting L in here doesn't help, because you just get L plus L, that's 2L divided by 2 is L. Well, that just gives me L as L. So what does it converge to? Well, simply taking the limit in the recurrence gives you L is a half L plus L. Well, that tells me nothing. That just says L equals L. So that's not particularly helpful this time. We know it's got a limit, but simply taking the limit in the original recurrence doesn't give me anything. However, I'm just going to observe now that if you take each term plus a half the term before it, then I can replace this with the average of the two terms before it, and then I'm adding in this one, and a half plus a half is 1, so I get an plus 1 plus a half an. Now that's very nice, because that tells me that I'm just bumping the terms down, and each term plus a half the term before it equals the next term down plus a half the term before that. And you can just keep repeating this argument over and over again until finally you get down to a2 plus a half a1, and we know what those numbers are, and that's 5 halves. So that means then an plus 2 plus a half an plus 1 is 5 halves. Now we know this has got a limit because it's a Cauchy sequence. Now I can take the limit in here, so that will go to L, that'll go to a half L, and we know the sum is 5 halves. I can add these together, we get 3 halves, and finally I can solve for L, and I get 5/3, which is 1 2/3, which is about 1.66666, which makes sense in terms of those first few terms we were looking at in the sequence. Now all that's quite involved. It's going to lead us to what we're going very shortly in the next recording, it's going to lead us to what is called a contraction. And we'll have a look at that in the next recording.